Say you're me in your math class, and today you're looking at strips of paper, specifically how to fold them into fifths. So you could just eyeball it and try to fold them into fifths, or you could use something cool. Fujimoto method, woohoo! You're gonna eyeball a fifth, and then fold in half again. Whoa, reducing the error, that's so cool. You know what else is cool? Flexagons. Flexagon time. Flexagons are strips of paper folded into closed loops that have multiple faces. You first learned about flexagons from Vi Hart way back in 2012. Ew, middle school. She learned about them from Martin Gardner, and so on, way back to Arthur Stone and his friends back in 1939. It's a maspiration train. Anyways, you keep folding your triangles, and finally you have a loop, and you close them up, and you have a hexaflexagon. Great. Now all you need is tape. Oh no, your teacher comes by and says, "Rawr, don't use my tape." Okay. And you put Flexagons aside for the moment. You find some tape later and you decide to show your friends how cool Flexagons are. So if you color this side green, then if you flex it, you show them there's a whole nother side. So that one's white and you decide to color it yellow. But not only are there that green and yellow side, but if you flex it again, there's a third side. What? You tell your friends because it's a flexagon and it's in the shape of a hexagon and it has three sides, is a trihexaflexagon. You color the third side pink, and then you can show them the whole loop. Pink to green, green to yellow, yellow to pink again, and again pink, green, yellow, pink. Rad. Because your math class is so cool, you get the chance to do a project and you decide to investigate flexagons more. You decide to make a six-sided hexaflexagon or a hexahexaflexagon, so you tear another strip of paper and you fold it up. This time you're going to need 18 triangles, so you have 1, 2, and so on, making more and more triangles. Triangle time! And finally, you're at 13, 14, 15, 16, and 17. Uh-oh, you're short. You count again to make sure, but you find that the disastrous truth is true. You only have 17 hexaflexagons, and you decide to investigate the ratio of size to avoid this mistake in the future. We know for the hexahexaflexagon we want to have 19 triangles, because we want to have 18 across and then one more to glue. There are going to be these little pieces on the end, and because of the way the triangles are arranged, they're going to be half of them on one side and half on the other, so 10 triangles total. If we call the base of one of the clearly equilateral triangles x, then we can see the total width of the strip is 10x. We know that because of the ratios of a triangle, y'all remember trig, that if we call the base x, so half of it is 1/2 x, and the altitude is square root 3 over 2, nice. So 10 is to square root 3 over 2 for the ratio of our paper, and so we can see that's the same as 20 is to square root 3. So our whole strip of paper is going to be 11 inches long, and that needs to be proportional to that same square root 3 over 20 value times 11. And typing that into a calculator, we can see that it's equal to 0.95, so our paper should be 0.95 inches tall. Armed with this knowledge, you proceed to make a hexahexaflexagon, so you tear your strip, then you're going to fold it all up into those 18 triangles you calculated for so carefully, tear, and you have your perfect ratio. All yes, for a hexahexaflexagon you have to fold the strip of paper onto itself and then take the folded strip and fold in what appears to be a normal trihexaflexagon, but it actually has an extra layer. And then here we glue the 19th to the first, and it's been done. Hexaflexagon. Aw yes. You know what's cooler than a hexahexaflexagon? A hexahexaflexagon with colors. Labeling time. That's pretty nice, but we can't have nice things because we like math, so you decide to make a diagram. So you can see the green side goes to the pink side, and the pink side goes to the orange side, and they're pointing in, and that's important because it helps differentiate the different shapes. Okay, cool, so orange to green, and then green goes to yellow instead of pink. And then yellow goes to orange, but this is a different orange, as you can see by it's going outwards. Cool, so back to green and pink, and now we're going to flip pink. Instead of going to orange, it goes to magenta, and magenta to out green, which is somehow different than the other in green. Pink is going to go to orange, and orange flips to blue, and blue goes to out pink, which can go back into orange. What's interesting about the hexahexaflexagon is because of the extra layer, Some of the faces are able to flex in 2 different directions, specifically the ones on the inner loop. In this case, green, pink, and orange. Nice. So that wasn't complicated enough, so you decide to make a 12-sided hexaflexagon. For this, we're going to need 37 triangles, and you can see that they're increasing by multiples of 9, so first 9, 18, and now 36 plus a gluing side. It happens to work out ratio-wise that dividing a piece of paper into 6 will give us 7 triangles on each, and that works out really nicely. And because this is a Viehart style video and not a number file style video, you can investigate that on your own. You make a 12-sided hexaflexagon in almost the same way you make a hexaflexagon, except instead of winding the strip of paper onto itself once, you actually wind it over onto it a second time. Cool. So you're a mathematician, so you know it's diagram time. You're still going to have that inner loop of 1 to 2 to 3, and now you're going to flex. You can see that 1 can go to 6, and 6 goes to 3. And this is an outer 3, just like you found in the hexaflexagon. And 3 returns us back to 1. 6 can also take us to 7, which can take us to a different outer one, just like you saw with the hexaflexagon. And now, if you flex again, you try to flex 1 the other direction, but you see there are enough layers, so you can only go back to 6. And 6 can go to 3, which can also take you to 8. And 8 takes you to 6. This 6 can also only flex 1 direction. Nice. So now if you flex 6 back to 3, and 3 to 1, 1 to 2, let's see what 2 has in store for us. 2 can go to 5 to 1 to 2 to 5. Wow! And 5 can also go to 9, which can also go to 2. Whoa! You notice this diagram seems to have the pattern of each face having 2 faces connected to it, and this going 3 layers deep, and you wonder whether this pattern is going to continue. You continue filling out the diagram and find this pattern does hold. It's nice and fractally. Neat! After your long mathematical adventure, you decide hexaflexagons are super cool.